National 5, welcome back to another episode. Today I'm going to be talking about dynamics and specifically distance and displacement and velocity and speed. So I'm going to demonstrate what it would be to get from the top of this hill to that bottom bit there using distance, okay? So I'm going to do that now. Alright, that was distance, okay? So I travel the distance in some sort of time, that is speed. But what is displacement and what is velocity? So let me show you what displacement is. It's the shortest distance between 2 points. I'm going to show you that now. See that? Shortest distance between 2 points. The shortest distance between 2 points. So my velocity is the displacement divided by the time. Alright, so we're going to be talking about a whole bunch of stuff like that today in today's revision. I'm a little bit out of breath. So we'll jump onto the PowerPoint in 3, 2, 1 and go.
National 5, welcome back to Mr. Bill's Physics. Hope you enjoyed my little time out in the snow and that you have been enjoying your time out in the snow last week. But today we're talking about dynamics, and specifically we're talking about 3 different things: vectors and scalars, average and instantaneous speed, and vector diagrams. Now vector diagrams are probably one of the most difficult parts of the course, so that is why we're spending lots of time on that today. So first things first, vectors and scalars. So you should have this table somewhere in your booklet, in your dynamics booklet. And we should know that a scalar quantity is defined by only its magnitude, which is like a size, a value, and a vector quantity by its magnitude and direction. Okay, so it's a value plus a direction. So normally past paper questions will ask you this, sometimes multiple choice as well, like name the thing that's a scalar or name the thing that's a vector. So we should know every single one of these things on the table. A scalar is something like speed, distance, time, temperature, energy, and mass. And something that is a vector that would have a direction is velocity, displacement, force, weight, and acceleration. All of those are vectors, and you have seen a lot of those things in the course. Now, speed and velocity in terms of distance and displacement. Speed, as I was talking about in the video, is distance, speed, time. That's very easy. You should know that by now. Speed is meters per second, time is seconds, distance is meters, and that is the total distance travelled by something and the path that it takes. Velocity is the displacement. Okay, displacement, remember, is the shortest distance between 2 points. And velocity is measured in meters per second and time is measured in seconds. Okay, so a good example of this, just as a wee side note, is like if I was to go from here up to Aberdeen, I would have to go follow a distance, i.e. I'm having to go on the motorways with my car. Obviously I can't do that because of the lockdown. But if I was to do displacement, it would be like if I was flying from Glasgow to Aberdeen, it would be straight across from one point to another. Okay, so that would be the displacement, and the distance would be what I actually travelled. Okay, so remember this here, velocity is a vector and therefore an angle or bearing must be given. We use bearings in physics, okay? So again, we're going to come on to an example of that later. But let's do an example here. A runner sprints 100 metres north along a straight track in 12 seconds and then takes a further 13 seconds to jog 20 metres back south towards her starting point. So what distance does she run during the 25 seconds? What is her displacement from starting point after 25 seconds? What is her average speed? And then what is her average velocity? So the distance is, remember, just the total distance. So I've got the answers here. So the total distance is 120 metres because 100 plus 20 is exactly what she travelled. That's her distance. Her displacement, though, is only 80 metres north. Remember, we need to have a direction when we talk about displacement, and she is 100 metres north, and then she only goes back 20 metres south. So she's only actually travelled 80 metres from the starting point. But she's still further north than she was, so it's 80 metres north. And then distance, speed, and time. Remember, distance for the speed, it's just the distance, so it's 120 divided by the 25 seconds she took to travel, and that's 4.8 metres per second. And then the displacement is velocity equals displacement, which is S. So remember, the displacement is S, not d. Okay, S. And it's not speed, it's displacement. And that's 80 divided by 25, which is 3.2 meters per second north. Okay, because we need to have that direction in there again. So that was that. Now, let's move on to average and instantaneous speed. So for average speed, you will probably be aware there's average speed cameras about, particularly on the way up to Perth. I think there is some, and Aberdeen as well. There's average speed cameras, and basically they take a distance, a very large distance, and the time it takes for you to do that distance, and then it calculates the average speed. Okay? Now, we can do an example of average speed, which is calculate the average speed of a car which travels 2,400 metres, remember, a large distance, in 5 minutes and a larger time. Okay, so it's over a longer time and a longer distance. Then to do that, it's just going to be speed equals distance divided by time, 2,400 divided by 5 times 60, because we need to get into seconds, which is 8 metres per second. Okay, remember, it's not a vector, so it does not need a direction. Now, this is important. There will always be a question asking something about average speed experiment, velocity, instantaneous speed experiment, or acceleration experiment. We're not looking at acceleration today, but you do need to know these experiments. So what would you have to do? You have to, 1, measure the distance travelled using a meter stick or trundle wheel. 2, measure the time taken with a stop clock. You need to make sure you add in the unit that or the measurement device that you're using, and then use the equation distance equals speed times time. So memorize those 3 points for me, please. That is so, so important. Okay, you must mention what you measure both of the relevant quantities with. You must mention the stop clock and the meter stick. For instantaneous speed, instantaneous speed is the speed in an instant, in that moment of time. So when you look at your speedometer, that is giving you a speed at that moment in time. Okay, so it's at an instant in time. So in this one here, we've got a light gate, and the experiment is very similar to before, okay? But instead of doing a larger distance, you normally find the distance of the trolley gate. So you see the trolley, the blue car, there's a little gate on the top. That thing there is the distance that we use to find instantaneous speed. And it's the time it takes for that light gate to cut that little bit of card. Okay, so if we can find the distance of that card and the time it takes to cut that light gate with that card, that will give us the instantaneous speed. Okay, so again, this time we need to measure the length of the card using a meter stick or something equivalent, measure the time taken with a light gate connected to a computer, okay, and then we use the equation D equals VT again, okay. So that is something, again, you need to memorize. Please memorize that for me. Thank you. Right, an example though, a car of length 4.5 metres passes through a speed trap light gate in a time of 0.18 seconds. If the road along the car travels is 2,500 metres long, calculate the car's instantaneous speed as it passes through the trap. Now remember, we do not use a long distance, so 2,500 metres would be for average speed, but we do not have the time it takes to travel the 2,500. So the two values are the length of the car, which is 4.5 metres, divided by 0.18 seconds, which gives us 25 metres per second. So that is the instantaneous speed at that moment in time. Okay, so hopefully that makes sense. Basically, memorise those experimental procedures and you should be absolutely fine. The last bit though is vector diagrams. So vector diagrams are extremely important, and I've not got an example on this one because we are going to go through kind of a major example here. So we need to make sure that in vector diagrams we do magnitude plus a direction. So this is where we have Pythagoras and also where we have trigonometry. Okay, so Pythagoras and trigonometry. So let's look at an example of a girl walks 30 metres north and then 40 metres west. Calculate her resultant displacement. Resultant is a fancy word for basically from the start to the finish point. Okay, so if I looked at this arrow here, we've got a start point, which is the bottom of the 30-metre arrow, and the finish point is the end of the 40-metre arrow. So if I was to draw a line from the start to the finish point, that is her resultant, and that would be the displacement. Remember, the shortest distance between 2 points. So we need to draw a diagram. Always draw a good diagram. We start with the 30 metres, okay, because that's the first thing that's coming up. 30 metres north, we go up, and then we go 40 metres west. Okay, so we've got our diagram. That's the first thing you must do. Then you draw the resultant. As I said, that is the resultant there. So you need to draw the resultant. You can do a dotted line. You can do a line with 2 arrows, as long as you know that that is your resultant displacement. Okay. Now, as you might come on to later, this can also be things like speed. This could be things like force. It is still the same physics of finding out the resultant, except the units might change. Okay. So first of all, we have to find Pythagoras. That should be straightforward. It's just a squared equals b squared plus c squared. So you do 40 squared plus 30 squared, and then do the square root of 2,500, which is 50 metres. You should probably know that because it's a Pythagorean triplet. But 50 metres is probably worth 2 marks. That would be 2 marks in a past paper question, and that's the easy part that I'm expecting every single person to be able to do. However, this is where it gets tricky. We need to now draw the bearing onto our diagram, because remember, it's a vector. Displacement, velocity are vectors. We need to add a direction. So we need to find out a bearing. Now, in this triangle, something is travelling almost northwest. We don't know exactly what the angle is, but we know it's roughly going northwest. So we know the bearing is going to be fairly large, because the bearing is from the north all the way around in a clockwise direction to where the resultant is. Okay? So I did this little example for my third years who are learning it, and it's a little bit fuzzy, but as you can see, we've got a whole bunch of triangles here. And basically, I would like you, whenever you're doing something, is wherever you put your triangle in, is whatever you need to use, the formula you need to use to calculate the bearing. Okay? So for example, if we go back up, this triangle here, if I was to sort that in like a jigsaw piece, that would be fitting into the 360 minus x, or minus the angle. That is going to give us the bearing. Okay? Now, what do I mean by that? Well, if I go down here, we were to use trigonometry and do x. We always put the x, or the angle, from where we start from. So we started from the 30 metres, so that is the angle, that is the angle we're going to find out. So tan x, it's always tan. It's never sin or never cos, it's always tan. So tan x equals the opposite over adjacent. The opposite of x is 40. 40 divided by the adjacent, which is 30. We need to find the inverse tan. And again, hopefully this makes sense to you, because this should be revision from maths and your physics. So inverse tan of 40 divided by 30 gives me 53 degrees. But look, to get the bearing, I need to do 360 minus 53. And why am I doing that? Well, remember my little technique is if I was to fit that triangle into one of the ones above, it would be the 360 minus x triangle that it would fit into. Okay, so whatever triangle you use, you can fit it into this diagram, and you should be able to find out the correct bearing that you need to use. Okay, so that is a little hint for you all. So 53 degrees, so the bearing would be 307. 307. So the final answer, the final displacement is 50 metres at 307. That would be your final answer. Okay? Now, that's us gone through it. Go back if you need to go back. Stop it at bits where you need to stop it. But that is exactly how I would expect you to do a question like that. That would be worth like 2 or 4 marks. And then you'd be asked to calculate things like distance, and then things like not distance, speed, and then velocity. If you're finding out velocity, you would need to use the displacement you just found out, plus then adding in the direction that you just found out as well, because remember, velocity is a vector. So, what do we need to remember? First of all, for displacements, velocities and forces, because they're all vectors, you need to first of all draw a diagram and make sure that all your arrows are top to tail, i.e. it goes from start to finish with all the arrows in the same direction. Number 2, calculate the magnitude using Pythagoras, and then we calculate the direction using tan x equals opposite over adjacent. And then we must remember to put the triangle into the right diagram to find out how we find out our bearing. Okay? So that there is everything. That is the vector diagrams. So I hope that makes sense, National 5. This is the most difficult stuff. So if I've given you some good questions on this, if you can work out these questions, you'll be onto a winner. And if you can do it for the vectors, you can do it for forces, you can do it for velocities, you can do it for everything. Okay? So very well done again. We're doing well, National 5. We're now just revising, getting it all done. So again, very, very, very well done for all the work you're putting in, and keep it going. Okay, see you later, National 5.